Hi everyone, welcome back to Power System classes. So in the last class, we were looking at the transmission system, and we were looking at the the most important, like one of the important part of transmission system, that is basically the insulators. Okay. So today also we will be actually continuing discussion insulators to a bit, and actually we will be closing the insulators today, and we will actually start the power system transients. Okay, which is the most important part of power system. Okay, so I will share my screen now and we can start. Okay, so we can start with the we can start where we end the last class. That is basically the insulators. Okay, so we'll be continuing discussion of insulators. Okay, in the last class I have mentioned about the different types of insulators like pin and suspension type insulators. So today we will be actually discussing about the the suspension type of insulator and mathematical actually analysis of that. Okay, assume this to be the tower, okay, or the nearest ground. Okay, so tower is the nearest ground. So I am just representing it like this. This is the nearest ground. So basically, each and every insulator is basically a capacitor, right? Because the current cannot flow through it. Only there will be potential difference will be there. So each insulator I am actually representing as a capacitor. Okay. So what this basically means is, assume that there is one insulator here, and another one is here, and another one is here. Okay. So assume that these three are basically insulators. So now what we will do is, this one is the capacitance between these two. Okay. And this is the capacitance between these two. So if there are n insulators are there, so there will be n minus 1 capacitance. So these things you have to remember. Okay. There will be n minus 1. So this type of capacitance is basically known as a series capacitor. Okay, so this study of these things are actually initially carried out by Peake. Okay, the scientist name is Peake. One of his famous paper is there, that is in 1904. Okay, so he has derived this mathematical expression for everything. What I am going to derive now. So this is basically derived by Peake. Okay, so he was the first one to observe all these kind of things. So it's almost like 1 century ago. Okay, so this is basically the capacitance existing between these two disks, and there will be one. So this is the ground, right? So capacitance exists between any two conductors which have a potential difference, right? So this is basically a ground, and this is also a ground, right? So there exists a capacitance between this ground and this particular insulator. Okay, let's rename this as this. This is known as the self capacitance. Okay, so capacitance of each insulator with respect to ground, that is basically known as the self self capacitance of each disk. Okay, so assume that this configuration is like this. So here is the conductor. Okay, so the conductor will be actually coming here. So here is the conductor, and here is the ground. Okay, so these are metals. Okay, so we can write like this. This current is I3. Just for the sake of convenience, this current is basically I3. This current is again split into I2, and this is also I2. So I2 splits into I1, but small I1, and this is basically okay, capital. So this current is actually flowing like this. So I3 is there. So this current will be I3 plus I3. Okay, this is the largest current. So a part of the current is actually flowing to the ground. Okay, so this is actually less than this. This is again less than this. Okay. So as the we move from conductor to the ground, the current actually starts decreasing. This is very important. Now we can write like this. I2 is basically equal to I1 plus I1, right? We check here, I2 is basically equal to I1 plus I1. So we can write V2 omega C, correct? That is the current through this one. Okay, we actually name this as C, 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 C1, C1, C. Okay, like this. So these are the actually self capacitance, and these are the mutual capacitance. Okay. V2 omega C equal to I1 plus I1, right? So assume that this potential is V1, potential is V2, and this potential is V3. Okay, these are the potential across each disk. Okay, so this one like this. So that means V2 omega C is I1 is basically V1 omega C plus this I1. So that will be V1 omega C1, right? So if we check here, this point is also having the same potential, right? This is almost connected parallel, right? So V1 omega C1. So that means V2 omega C is basically, if I check here, that is V1 omega into C plus C1, right? This V1 omega C plus C1. So if I take C1 equal to some K times C, okay, then we can write like this. V2 omega C will be equal to V1 omega C into 1 plus K, right? Because C1 equal to basically K times C. So, so that means what we can see is V2 equal to V1 into 1 plus K, right? This is the first equation, right? So V2 is equal to V1 into 1 plus K. Similarly, we can derive V3 in terms of V2, then again V2 in terms of V1, okay? So we can write V3 equal to V1 into 1 plus 3K plus K square, right? So similarly, we can find for any Vn, okay, like this we can actually find this. So if we check here, so what is the voltage across each disk? So just check here, okay, I will write it here, next page. So basically V1 equal to V1, V2 equal to V1 into 1 plus K, and V3 equal to V1 into 1 plus 3K plus K square, right? So we know that C1 equal to some K times C, right? So this will be always positive, right? Because capacitance cannot be negative. So that means if K is always positive, then V2 is actually greater than V1 and this is greater than V3, right? So what is happening is, so assume this is the conductor, there are 3 capacitors, okay? And here it is the conductor. This potential V3 is actually greater than this one, right? V2 and actually greater than V1. That means, and if you look, this is almost going to a not exactly linear, right? So it is almost going like something like a parabolic or higher order, right? So we'll get something like the most voltage will be actually concentrated here like this, something like this. So more and more voltage will be actually concentrated near to the conductor. So what is happening is that these insulators, which is near to the line, that will be more stressed, right? These insulators will be more stressed. Because the potential is actually almost all the voltage is actually coming across this particular thing, right? So that means these are actually containing very large potential. So what is happening is that the string efficiency will be very, very poor. String efficiency will be very poor, right? So you should remember this. So the string efficiency will be very, very poor. So we can define what is a string efficiency. So string efficiency is eta string. It's basically voltage across string. That's the total voltage across the string divided by n into voltage nearest to the conductor. Okay. So that is basically the meaning of string efficiency. All right. So if we check here, the string efficiency here is the total voltage is V1 plus V2 plus V3 divided by 3 times V1. Sorry, nearest to the conductor, right? So 3 times V3. This is basically the string efficiency. So we already know that these are not equal, right? So efficiency will not be 1. So what if V1 equal to V2 equal to V3? That means we can write eta equal to V1 both equal. Right? So that means the top will be 3V3 and denominator will be again 3. That is basically 1. So the maximum string efficiency we get from this condition. Okay, all the voltages are basically equal, or actually it is a uniformly distributed. Okay? All the voltages are equal. So this will be added here and like this. So the total potential actually will be actually like this. So this is basically known as string efficiency. So what happens if the string efficiency is poor? So string efficiency is poor, then what happens is that more and more voltage will be concentrated near to the capacitor, near to the conductor. So that means these will get flashover. Okay, so there will be flashover near to the conductor. Flashover near to conductor. So you should avoid this. So what are the things by which actually we can increase the string efficiency? Things by which actually we can increase the string efficiencies. First one is basically known as longer cross arc. Okay, just remember these things. And second one is known as grading of capacitance. So what I have mentioned is all the insulators having same capacitor, right? So what if there is actually a grading in capacitor? So one of the insulator might have a higher capacitance than the other. Okay, that is basically known as the grading of capacitance. And third one is known as the guard rings. These guard rings are important because so what the guard rings basically do is that what we really want, the value of k should be very close to 0, right? Then we have what is so V1 V2 equal to then V3 in sorry V2 equal to V1 into 1 plus k, then V3 equal to basically V1 into 1 plus 3k plus k square, right? So what if this k is very nearly equal to 0? That means V1 equal to V2 equal to everything will be same potential, right? So what is this basically k? K is basically C1 equal to some k times C, right? So that means this series capacitor or the capacitance to the ground should be actually very, very small, right? This is very, very small, then actually this can happen. Okay. So one way of doing this is actually we can reduce the current flow through this capacitor, okay, by connecting one more shield, okay, near to the ground. So that means now it will assume that these are the two things. This is the one ground capacitor and this is the another one. Okay. So what we will do is we will connect some two more capacitors. Okay. We will connect one more capacitor here and one more capacitor. So now what is happening is these two capacitors will get parallel, right? Sorry, this current flow will be actually divided series, right? That means this actually what is happening is this actually the current flow will be actually because initially this was the current, now the current gets shared like this. So the effect of the capacitance will actually comes down, so that the effective C1 actually comes down, so that this K will be nearly equal to 0. So this process is known as a guarding ring. So we will actually keep some kind of a rings very close to the conductor, like something like this, so that there will be another capacitor, another current flow. Okay. can check the figures of the guard rings, how it is actually working. So there will be something like this. You can just check the insulator, what you normally see, there will be some kind of a metallic thing. You just keep it like this. These are basically known as the guard rings. This is basically used for improving the string efficiency. Improving the string efficiency. Okay. So you can write down all these things. After 1 minute, we will start again. So I hope you understood the things. So by this, actually, we are actually stopping the discussion regarding the transmission lines. Okay. So we'll coming back to this transmission line once actually we study about the something known as surges. Okay. So because we'll be studying the lattice diagram and everything. So that will be covered in the next class. So we will be now looking at starting of power system analysis. Okay. So these things are the introduction, or these were the infrastructure for power system. So we just look at the infrastructure, or what are the exact things what we actually, the physical things what we actually use for the power system. Okay. So apart from generator, the main thing is actually the transmission system. Okay. So I have covered different types of transmission, the conductors, insulators, capacitors, and everything. Okay, regarding the transmission system. Now we will be looking at something different. That is basically we will be looking at the power system analysis. Okay. So what is basically the important aspects of power system analysis? So we will be actually looking at here. We'll start with per unit system. Then we will look at transients. Then actually we will look at, after transients, look at voltage control and frequency control a bit. Okay, because we will study most of things in machines, voltage and frequency control. So these things will be covered more in synchronous machines. Okay. Then load flow and economic load display. These are the 5 topics we will be covering in power system analysis. Okay. So then we will go to stability, issues with stability and other things. Then we look at a small bit of something known as this distribution, and then we will stop the power system classes. Okay. So these are the important things you have to look at in a power system analysis. Okay. So we'll start with per unit system. So why we need a per unit system, or what is the importance of per unit system? Okay. So we actually normally say something with respect to something, right? That is more convenient to say with respect to, like we normally say percentage. Okay. So these are actually percentage, with respect to 100. So 5% or 3%, like, so this is basically with respect to 100. and we are actually, then we will say specific, right? So something like specific gravity is there, specific mass is there, some some other specific quantities are there. Then we will say something like relative. There is a relative density is there, then relative mass, relative acceleration. So everything we actually compared with something else. Okay. So this per unit is also something like this. A per unit quantity is a physical quantity expressed as a fraction of its base quantity. Okay. So that is something very easy to understand. So we can say a lot of things with respect to something like a reference. Okay. So we normally say our normal temperature is 25 degrees Celsius. Okay. So everyone knows this. Like everyone in the whole world knows this. So I am saying the temperature in India, T India, is basically 30% more than normal temperature. Right. So everyone knows it is 25%. Right. So 30% more means 30 by 100 into 25 plus 25. Right. That is basically T in or the Indian term. So that is we are actually something with reference to 25. Right. So 25 is taken as a reference. So similarly, we can do anything. We can actually, if you look at the density of the water is taken as the reference for everything. Then if you take epsilon 0, that is taken as a reference. So epsilon of any other thing is actually said as a fraction of epsilon 0. Similarly, mu 0, this the mu of any material can be represented as a fraction of mu 0, right? Or as a product of mu 0. So that's how we are actually defining. So one of the important thing is if you check, if the epsilon r of paper is 3, okay. So that means what is the original epsilon of paper? That will be 3 into 8.85 into 10 raised to minus 12, right? So instead of saying epsilon of paper is 24 into 10 raised to minus 11, we say epsilon r of paper is basically 3, right? That is very convenient now because if you make a table and everything, we can just put 3, 3.5, 2, 1 like that. No? So that makes our calculations much simpler. So one of the important aspects with per unit system is that it makes our calculations much simpler. So, but nowadays what is happening is that nobody knows how to do per unit, right? So most of the people who study BTech, they don't know the importance of per unit system because so that's why in gate, even if you see very large numbers like 6600 kilovolt or something or like this, don't worry, take this as reference. So all other things will be in a per unit. Okay, so that's why in power system, per unit system is very important because in power system we actually deals with transmission and distribution where the voltage is so large, like 765 millivolt. Okay, megawatt. So 765 volt, megawatt. So that means we have to put 765 and 6 zeros. So how much time it will take for us to write this in an exam paper, right? It will take a lot of time. So what we do is we will take 765 megawatt as one. That is the base. This is the base. So like 10 megawatt will be how much? 10 divided by 765. This is also a small number, right? So we are saying the voltage in our some places we found it like 0.5 per unit. That is we already know 1 per unit is 765 megawatt, right? So that is we can just multiply with 0.65. Then so we can avoid all the complex numbers. Okay, all the all the complex things what is actually coming here. Okay, so that makes this very very simple. Okay, so we can actually do the things very easily with a per unit system. Okay, so what are the different bases we have to consider in a power system? Actually, there are 4 important aspects are there in a power system, okay, or the 4 important electrical properties. The first one is voltage. Second one is basically current. Third one is impedance, Z. And fourth one is power or S or MVA. Okay, the apparent. So we have to take any 2s base. Okay. So if you take voltage, we can take V or kilovolt or something or megavolt or anything. Current is basically I. Okay. That is Z base. We take V base and I base. Right. So Z base will be V base by I base. Right. So similarly, what is MVA or S base? S base will be V base into I base. You should remember this. This S base is for like real power and reactive power. Okay. So there is no kW base. There is only S base, right? Or MVA base. There is no kWA base. Okay. So because kW is actually a factor of this one. So that's why we are taking the whole S base. And there is no kVAR base. Okay. So the base will be actually similarly here. There won't be any R base, any X base, or any like XL and XC base. So everything will be actually we will be considering as Z base. Okay. So 1 ohm, like if you are saying some 10 ohm is the base, then 1 ohm will be 1 by 10 per unit, right? So 100 ohm will be 10 per unit. 1000 ohm will be something like 100 per unit, or 0.1 ohm will be something like 0.01 per unit, right? So like this, we have to divide by 10 and multiply with 10, so we'll get the per unit. If you want to convert it back, then just multiply with the base. So V per unit, sorry, some number, something A in per unit can be written as A in magnitude divided by A base. Right. That means A in magnitude is basically A per unit into A base. This is very important. Right. So just look at this. So we can, if we take into, okay. So we can take. So what is basically kV square divided by MVA? We are actually taking this and this as base. Okay. So voltage in kilovolt and S in megawatts. Okay. Sorry, S in MVA, megavolt ampere. So what is this? This is basically K square is basically M. MV square divided by MVA. Right. This M and M will get cancelled. V and V will get cancelled. That means V by A. That is what is, this is actually V base. This is actually like ampere base. Ampere base is basically current base, I base. The V base this is Z base, right? And what is MVA by kV? That will be in kiloampere, or I base in kiloampere. What will be, so we have to put everything, we will get everything in kiloampere, right? So our base is basically 1000 times like an I base in ampere or something like that. So we can, this much kiloampere will be our base. Okay. So if we can take any 2s base, and we can actually find other two from this one. Okay. So we cannot take 4 actually different bases. Okay. So even if you take some 4 numbers, they should satisfy these 2 equations. Okay. What are the equations? This is and right here. What are the equations it should satisfy? If you have V base, I base, Z base, and S base. The equation it should satisfy is V base divided by I base should be equal to Z base. Similarly, V base into I base should be equal to S base. We can choose any two. We can even choose these two, right? These two as base. So if these two are the base, then from these 2 equations actually we can find this one. Okay. So if we just multiply these two, so what will be? That is Z base into S base, right? That will be V base by I base into V base, right? Into I base. This will get cancelled, right? That means Z base into S base is basically V base square. Right. So that means V base equal to root of Z base into S base. Right. So we got the value of V base. Now we can find the value of I base. So I base is equal to V base divided by Z base. Right. That is I base is equal to, what is V base? Root of root of Z base into S base. This V base divided by Z base into S base. Right. Sorry. So I base equal to V base by Z base. So I base is equal to V base is basically root of Z base into S base divided by Z base. So that is basically I base equal to root of S base divided by Z. To take square of this, I square equal to S base divided by Z base. So S base equal to I square into, right. So these are the basic equations we can actually derive. Everything we can derive from these two. Okay. So we can take any four. These are the four the basic quantities what you have to consider. And while you consider, you cannot randomly choose these four. You can randomly choose any two, but the next two should satisfy this equation, this set of equations. Okay, that is very important. Okay. So I hope you understood the thing. We can just write down these things, and after 1 minute, I will just start the other aspects of per unit. Okay. Okay. Now we can check about this. What I what I have said till now is basically for a single phase system. Okay. So we can look at the 3-phase system. So 3-phase, then V base is basically V line. V base is basically V line. Okay. And I base is basically I line. Then S base basically root 3 into V line, I line. Okay, these things you should show. V base equal to I line, I base equal to I line, S base equal to root 3, V line into I line. Even if it is star or delta, it doesn't matter, because for star and both star and delta, power is basically root 3 into V into I, right? So these things you have to. Okay. Now we just assume that we have some system like 500 MVA, some 200 kilowatt. Okay, and the per unit impedance is something like Z per unit, something like 0.35 or something. Okay, assume that. Then actually we have another system. Okay, this is we have another system of 1000 MVA and 250 kilowatt. Okay, so what is the equivalent Z impedance of this one? This is a normal question what is asked in most of the the exams, right? This is somewhat known as base changing formula. Okay. somewhat known as base changing formula. Okay, so we can write like this. What is, so we are taking these things as old. Okay, this is also old. This is new. This is also, this is basically Z per unit. So we know the value of Z per unit old. From there we have to find the Z per unit. We can check this. What is Z per unit old? So that is basically Z divided by Z base old, right? If you check here, what is this? Z per unit old means this Z is the same thing, right? This is in magnitude, right? This doesn't change with the base, okay? Because I have something like 1000 ohm. So when one base it is 1000 ohm, second base also it will be 1000 ohm, right? This is because this Z is not going to change, right? Similarly, if you check here, this is Z per unit old. So what is Z per unit new? That is Z, because this doesn't change if you change the base, right? That is Z base new, right? So this will be. So if you multiply this, if you check here, that is Z per unit old into Z base old will be Z, right? Similarly, Z per unit new into Z base new will be still Z, right? So we check here. That means the RHS of these two equations are now same, right? Both are actually Z. That means the LHS will be also same. So now we have to actually equate the LHS. So what is this LHS saying? Z per unit old into Z base old equal to Z per unit new into Z base new. Right. So what we have to find out? We have to find the Z per unit new. So Z per unit new is equal to Z per unit old into Z base old divided by Z base new. Right. So to just check here, this is the base changing equation. This is something known as the base changing equation. Something known as base changing equation. Okay, so you should remember this. Now we can actually write what is Z base old. That is kV old, right? The whole square divided by MVA old, right? So similarly, what is Z base new? That is kV new the whole square divided by MVA, right? So if we substitute this together, what will be? That is Z per unit new will be Z per unit old into Z base old is basically kV old the whole square divided by MVA old, then divided by Z base new. So that is we have to multiply with. So MVA new divided by kV new the whole square, right? So that means what is happening here is Z per unit new will be equal to Z per unit old into kV old divided by kV new the whole square into MVA new divided by MVA old, right? This is basically something known as the base changing equation. So you should remember, because this is asked for a lot of times in this PSUs and other examination. So in both the cases, if kV old and kV new are same, and if there is only difference in the MVA, then what we can write? Then Z per unit new equal to Z per unit old into AV old divided. So these are actually same. This will get cancelled into MVA new divided by MVA old the whole square. Right. So this will be something known as Z per unit new. So Z per unit new equal to Z per unit old into MV new by MV old the whole square. Okay. So these things you should remember for the examination. So don't by heart the equations, just remember this. Because in both the cases, even for the new, new base or the old base, the magnitude actually remains same. So that means Z mag is basically Z per unit into Z base, right? And this will be actually same everywhere. So Z per unit old into Z base old will be equal to Z per unit new into Z base, right? So just remember this. So from there actually we can derive this. So there is no point in actually mugging up these equations, because if you mug up these equations you will actually forget after some time. Okay, so better actually you understand these things. Okay, so that is the best part, actually you can do this. Okay, so I hope you understand the thing of actually per unit, and there is another aspect of per unit in power system. Okay, so assume that we have a something like a generation and distribution system. So this is basically a generator, and we have something like a transmission line. Then we have something like double circuit transmission line. So this is basically a transformer, double circuit transmission line. And we have another transmission or transformer. Then we have another transformer. Then we have many distributions, right? Like this. So everything is actually basically transformers. Okay. So we can take something like this. This is 765 by 11 by 765. Like so, we have to represent this in a single line diagram, right? Single line diagram basically shows the electrical equivalent of a power system. Or representation of a power system by passive components. Okay, that is basically known as a single line diagram, or we can just show everything. So we can actually model the generator as a voltage. Then we have to take this the capacitor. Okay, the inductor and the resistor, because we are actually working still in 50 hertz. So the capacitance of these things are irrelevant. So we actually for transformer we just consider inductance and capacitance. Then we have a transmission line, again inductance and resistance and inductance. Then again a transformer. Then again another transformer. Then series of transformers, like okay. This is the equivalent circuit. So for these things, actually, we can directly put the values of transmission line and generator. Okay. So what is impedance of this? Okay. So now the great confusion will come now, because should we refer this the impedance is at R, L and R of this, the effective L effective and R effective of this transformer refer to primary or secondary, because if you refer to primary or secondary, that means actually what is happening is, if you refer this to a particular primary or secondary, the impedance value is different, right? Because there will be some kind of a transformation ratio will be playing if you refer to primary, refer to secondary. But if you refer everything in per unit, so the per unit value is actually same for a transformer in primary and secondary, right? That means we got only one values. Okay, that means we can write everything in per unit now. So, and we take which is the largest value, that we take as a base and convert all other things with respect to that. Okay, So that means now everything can be represented very easily, right? Else, if you represent this, we have to say to the people that this transformer is having, like, 0.4 ohm resistance, 0.5 ohm resistance, and 0.54 millihenry referred to 11 kV, right? Or we have to say other way, 0.5 ohm and 0.4 millihenry referred to 765, right? So instead of that, what we say is, we say R equal to 1 per unit, X equal to some 0.5 per unit or something. So that means this is actually in per unit. So even if you refer to primary or even if you refer to secondary, the per unit value actually remains same. So that's why the nameplate of a transformer, if you look, they will actually give you the R and L value, or the R and L value of the, that will be always given in per unit. Okay, 0.05 per unit or 0.03 per unit or something. So that will be actually in the nameplate. Okay, so that basically give you an advantage. Okay, you don't want to study, or you want to look at the where exactly the actually this impedance is referred. Okay, so this is advantage of primary. So if you take the 765 as the, the base, so this will be there. We have to convert this. So if you look at this, the voltage of this is actually referred to this particular voltage. So you will convert everything with respect to here. Then this is actually then we have to convert this, because this is per unit. Then we can take from there actually, from the new one we have to convert it again like this. So write everything in per unit. If you use base changing, then change the base for everything and make it a common base and do the calculations. So at the end, if you want to find the voltage drop across this transmission line, find the per unit voltage across this transmission line, then multiply with the base voltage, right? So that means it gives you more freedom in doing the things and more easily. Okay. So what now we can check the what are the advantages of transmission or advantages of per unit system. Okay. So this is very important. So what are the advantages of per unit system? Advantages of per unit system. So the first advantage is, here we are dealing with small number. Right. So we are actually looking at only 1 per unit 0.5. We are not looking at very large numbers like 1 mega or 2 mega like this. So we are actually dealing with very small numbers. Okay, then we can easily represent a transformer in the single line diagram. In single line diagram. Then typical values are already available. Okay, so typical per unit values of impedance, resistance are already available for each machine. So we just want to keep a copy of that. That's all. So from there, for each voltage rating, we can find what is the R, what is the L, and what is the C. Okay. And next thing is that it made the calculations very easy. So if you study for the gate or something like in a higher level examination, you should prefer doing everything in, per unit. Okay. That means actually this will give you an extra leverage of actually others will be actually putting all the zeros like this 365 0 0 0 0 0. You are not putting it, you are putting this one. Okay, so we can actually get lot of time from this particular thing. So in this way actually you can in your power system calculations, even the question also they will be actually giving everything in actually in per unit. Okay, so it will be very easy for you to do the things. Okay, so this is the most. This can be considered as a basic of basically power system. Because the power system almost works on this per unit system. Almost all the calculations in power system is actually done in per unit system. Okay. So you should have a good grip on per unit system. Have a good grip on per unit. Practice lot of problems in per unit system. So this is very, very important. If you look at the thing. Now, okay. So I have already mentioned that the transmission lines are actually very well exposed with the atmosphere, right? So there can be a lightning or switching impulse on the transmission line. Okay. So while explaining the short and medium transmission line, I have said that we are using a Lambda equivalent thing, and for a long transmission line, we are using a distributor equivalent thing. So what is the basic difference between Lambda and distributor? Okay. So assume that so every element or every element in power system is distributed. Okay. So every element is distributed. Even if you consider resistor, so this resistance is also distributed, right? So if I ask you, I will say 1 ohm. So where is this 1 ohm? This 1 ohm is actually across through this. Okay. This 1 ohm is distributed here in between the things. This is not at the center. Okay. So center is 1 ohm and others are 0 ohm. No. Like it is distributed here. So when can we consider something as lumped and something as distributed? So when are we actually doing this? Okay. So it depends on the operating frequency. Okay. So we can do some small example to understand. Just consider a 20 meter line. Okay. This assume transmission line of 20 meters. It's very, very small. Okay. 20 meter transmission line. Now we actually give a frequency of 50 hertz. Okay. Sine wave of 50 hertz. So what is the wavelength of this? So wavelength will be, what is the wavelength? Lambda equal to C by mu, right? C is 3 into 10 raised to 8. And this will be 50 hertz, right? So what is 50 hertz is basically 50. So that is 3 into 10 to the power 8. What is this value? You can just calculate. 3 into 10 to the power 8 divided by 50. So that will be 600 kilometers, right? So the wavelength of our normal AC coming in our home is basically 600 kilometers, right? That is basically the wavelength. Okay. So assume that this is only 20 meter, right? So this is basically 600 kilometers. Just think how big is this one compared to this. Okay. So if you are looking at this, if you are looking at this, so whenever you look, this will be always remains a constant, right? Because for every 20 meter, the voltage is almost remains constant, right? Almost small sections, right? We can actually divide this into this. So that means this is almost similar to a DC, right? So that means actually you don't want to consider the effect of frequency here. Okay, that's in a steady state we can do all the things which are similar to a AC thing is happening, right? So even if you look for a very, very, very long time, this will be actually remain same. There is nothing much effect is there. I will just give you one example. So if it is sine wave, so 20 volt is actually very, very 20 meter is actually very, this is 600 kilometer. Okay, it's a very, very small part of this here. Okay, so every time there will be some kind of an voltage here, and voltage that is actually coming there won't be much difference in the voltage at that particular line. So that means we can actually consider this as basically lambda. Okay, the element because assume that there is resistance here like this. So all the resistance, the current actually flowing through this is same, right? In that particular thing. So we can actually add all the resistance and make a single resistance like this. So that depends on the frequency. So the condition for lumping is the lambda should be very greater than L. Or in normal case, lambda should be at least greater than 20 times L. Okay. Then only actually we'll consider the lumping. Okay. Else we have to consider distributed thing. Now I will say you another example. What if the frequency of our AC, what you are giving is basically the time things are basically in nanoseconds. Okay. So frequency will be in gigahertz. You can consider 1 gigahertz, right? So what is basically lambda? Lambda will be 3 into 10 raised to 8 divided by 1 into 10 raised to 9. So the wavelength is now in we cut this 3 by 10 meters, right? That is 0.3 meter. Okay. So now just consider the same transmission line. Okay. Now consider the same transmission line of 20 meters. Okay. So here how many are there? Because 0.3, right? So 20 divided by 0.3 is almost 66 waves will be actually coming here. Right. So 66 total sine waves will be actually present here now. So that means now if you take this point, the voltage at this instant is this, at this instant is this. So every point the voltage is actually different or the current is actually different. That means we cannot actually lump everything together because same current is actually not flowing through all them, right? So that's why we are actually considering a distributed system, right? So it all depends on the frequency. So while we are actually lumping, we actually get something known as a algebraic equations. That is V equal to IR kind of an equation. But if this is a distributor, then we will get something known as a partial differential equation. So that's why in your short and medium transmission line, you can still use the network theory questions, but in this one you have to use something different. You have to solve the PDE for finding the thing. So all the network analysis things what you are actually studying is applicable only in static or quasi-static. Static means 0 hertz, quasi-static means 50 hertz, right? In these conditions, all the KVL. So if you think about KVL is valid only in this particular region, static or KVL, like quasi-static. Similarly, KCL also. So you might think why it is not valid, because your person might say that this is like KVL and KCL are the best one. Okay, like that defines the electrical systems. Okay, so the network teacher, for them it defines the electrical system, but for us it does not define, because if you go back to the Maxwell's equation, del cross E is equal to minus dou B by dou T, right? So if you convert this to time harmonic form, so this is the time harmonic form. So time harmonic form. This is basically minus j omega. So if you actually or we can do the other way. So this is 0 only when omega is very small. So del cross E is basically 0 only when omega is small. So del cross E 0 means integral E dot dl is basically 0, right? So this is basically the KVL. So if the KVL is valid, because E dot dl is basically V, so integral V is basically 0 or sigma V is basically 0, right? This is basically the KVL. So this is valid only when this omega is very small. Okay. So if the interest of area, the interest, our interest, the frequency of our interest is very small, then still we can use this network theory approximations. But if the area, our frequency is very large, that is, then j omega b is actually prominent, then this is not exactly 0, then we will get some other things here. So integral E dot dl will not be exactly 0. Similar to KCL also, if you check del dot j equal to minus dou rho v by dou t, right? This is basically the continuity equation. So del dot j equal to minus if you check here j omega rho v. Okay, that is 0 only when omega is actually very, very small, right? So that means surface integral j dot ds is equal to 0. That is basically sigma I is basically, right? This is basically KCL. So KVL and KCL are valid only for a very small frequency, okay, not for a very large frequency. So these things you should remember. So transients are, you have to study the transients because the lightning and switching frequencies are almost in like, microseconds. So that means we cannot use the lumped thing, what we study network analysis, for actually studying the transients. We have to look at it in a different way. Okay. So that different way we will be looking in the next class. So we'll be actually starting the transients in electrical power system in the next class. I hope you understand because these things are very important for you because this will actually gain you an upper hand in the interviews. Okay. So people will ask these kind of questions. Other questions everyone might know, like these are very important. So I hope you understand the session what I have explained, and I hope this will give you some insight about the power system. Okay. So we can stop it here now, and we can meet tomorrow. Okay. Thank you. Thank you, everyone.